Okay, so today's talk is about, still about matching under preferences, but on sort of tailored towards a more general framework of fractional matchings. I'm audible, right? Yeah, it's not echoing very much. It's good. Okay. So what is fractional matching? So in the more sort of this setting that we have seen yesterday and all the talks that we have encountered so far, we are basically the solution that we have, the matching is in its sort of pure form, like as we understand it intuitively. Every item as such is given to somebody in total, and that's about it. So obviously the most obvious examples of that are college admission. The seat is entirely belongs to one student, right? Job, traditional jobs where you are holding one job, the job is yours, that sort of thing. Now there are other situations where we are still talking about matching, and matching in the sense that we have talked about, where you want to assign items, agents to resources and so on and so forth, but this integral aspect of the assignment is taken away. So the most, I guess, in real life examples one can think of is part-time workers. So people who will have an 8-hour work day, let's say, but they're not assigned to one job. They're doing, say, let's say 2 hours shift jobs, right? 2 hours here, 2 hours there, and so on. And so you have a constraint that you don't want their work hours to be like more than 8 hours, but at the same time you want to assign them jobs that they can do. So the matching under the rationales behind matching under preference still hold here, but the idea is that that 8-hour work day is split into smaller pieces, and each of that piece is basically assigned to a particular job. So you can think, so this is one example. Then there are other things where, such as time sharing. What is time sharing? Time sharing is basically a certain amount of duration of the day or time is split between several agents. So that sort of a thing. Now these are the classical sort of matching scenarios, but you can think about a more not so traditional example, but it still works because it's again giving stuff to people, which is that there is one single item and that has to be split into pieces. Okay. So there is a huge amount of literature called cake cutting and cake division and so on and so forth. So this is sort of that there is one object that is the cake, and that has to be split among kids or people, all of you, and everybody has a preference on which side or sort of frosting they like and so on. So if you try to cut a cake in a birthday party, you'll see like there are people very strong preferences on frosting and so on. So that sort of a thing. Okay. Now these are some examples that you may or may not like. I mean, okay, let's not say may not like, because they do exist and somebody has to solve them and give meaningful solutions. One thing about the fractional matching setup that I want you to take away is that it's a more general framework of asking the same questions that we have looked at and answering them, but maybe from a completely different perspective. And that's the focus of today's talk. Okay. Right. So sometimes when you look at randomized outcomes, you're basically trying to think of them as lottery or sort of a mixed strategy where each of the deterministic outcomes are happening with some fraction of weight. Okay, so that's one other thing where these fractional matching framework comes in very handy. Okay. So again, so there's been a lot of, like, we are looking at older works and so on and so forth. So let's go back to the earliest that I can think of in the setting of matching under preference, where people sort of looked at fractional matching. So the way the matching is envisioned here is as an assignment matrix. So you still have, again, I am using the terminology from the original paper, you still have this bipartite type scenarios where you have men on one side, women on the other side. Think in terms of jobs and workers also. Usually jobs don't have preference over, but okay, you can think in terms of jobs and workers as well. So each man again has a subset of agents on the other side, in this case women, that he finds acceptable, and they have sort of some amount of preference over them. And the strict preferences as before, as we have seen. And similarly, symmetrically, it's the same case from the women's side. Each woman has a subset of men that she finds acceptable as acceptable partners, and she has a strict preference over that set. Now, each matching of men and women is represented as a matrix now, okay, where you assign, the matrix is a two-dimensional array obviously, and you index the rows as I and the columns with J's. And okay, so here I have used not IJ, but I have used men and women. So a matrix of this kind where XMW tells me what is the sort of the amount that the man M has been matched to woman. Okay. So in our traditional setting where we are talking about being fully matched, it is basically a 0-1 matrix. Okay. So if you think of a 0-1 matrix where every man can only be assigned to at most one woman, you can think of every column can have at most 1-1. Right? And similarly, every row can have at most 1-1, and every column also has the same property. So that's when we are back to the integral, the more traditional situation. If you allow fractional values, that's where the fractional matching scenario comes in. Okay, so why is it a matching, and why did I say at most 1-1s, right? I said at most 1-1 because that's what matching is. You either get assigned to somebody or you don't. In the fractional setting, what that would mean is you don't necessarily have the entries are not 0-1, but every column and every row will add up to at most 1. Okay? So exactly equal to 1 may or may not be the case. Strictly less than 1 is also possible, but this should happen. So this is like along each row should add up to at most 1. Similarly, on the other side, it should be every column should add up to 1. So when this happens, when Xij only takes binary values, okay, it's the normal matching scenario. Okay. All right. Yeah, and as before, yesterday, as I said, please stop and ask questions. I have a bunch of slides, but I don't necessarily have to go through everything. It makes more sense to make sense than just rush through things. So please stop and ask. So this particular setting dates back to these two works, Van der Waals in 89 and Rothblum's paper, which came out in 92. Okay. So I'll just write. So these are what we call constraints. Okay. So you want an assignment to this matrix X such that these constraints are satisfied. Okay. All right. Yeah. So one constraint missing, which you all should have pointed out, is if a man-woman pair is unacceptable, meaning this unacceptableness is like a symmetric property. If a man finds a woman unacceptable, and that's a vice versa condition, those entries have to be 0. Okay. Because okay. So now please tell me what would be a reasonable stable matching. So all I have talked about so far is matching, right? So how do I capture stable matching in this setting? You know what stable matching means in the integral setting. So how can I generalize that idea to stable matching in the fractional setting? Any guesses? Sorry, say that again. What will that capture?
That's a number between 0 and 1, and fractional matching you want to assign some number between 0 and 1.
Right, that's true, but how will I capture the notion of blocking pairs? Like you will not create a matching between I and J if, you will not create a situation where there exists a pair I and J which did not get matched, but they prefer each other more than all of the people that they are actually matched to.
Suppose that we have a preference over 2 items and more fraction was allocated to one item and the lesser one was the other. In the edge, if it is a blocking edge, then it could have been assigned
Okay. Okay. Yeah, that's a reasonable way of, okay. So, right, so before we go to the fractional setup, let's look at what it means in the integral situation, right? Okay, so this is a bit peculiar notation, I suppose, but I didn't know how to capture this. This basically means, this WXM, this thing means under the matching, under the matrix X, right? That captures the matching. What is the person that M is, who is the woman that M is matched to? So in the matrix X, look at the mth row, the position that has 1, that index. Okay, so it's a very long way of saying, but that's what this means. So if this happens, this means that the man M prefers W over whoever, this woman that he's matched to, and similarly if woman prefers this man M over whoever she is currently matched to, it's an obvious blocking pair. Right? That's the standard blocking pair condition when we have 0, 1 matrix. No? Okay. Right. Now, okay. So this is a situation that might happen when some people go unmatched. And you've seen yesterday that this can happen when the preference lists are not complete. Meaning, if there are people who don't find each other acceptable, there might be cases when some people go unmatched. And in that case, W definitely wants to be matched to somebody, right? So, and M already likes W more than his current partner, so this is also a blocking pair. So therefore, the blocking pair condition is more generally defined as preferring each other to whatever their current status is. By current status, it is implied that if you're unmatched, then you would prefer being matched to any of your acceptable partners. Okay, so this is this thing. And of course, both M and W have no partners. By the way, why do you think this is also should be included in the blocking pair? Just doing a sanity check. If both M and W don't have partners, why should that naturally constitute a blocking pair?
Because they could pair with each other.
Yeah.
We can make another matching from our.
Okay. Okay, basically the definition is that they are both unmatched, they would prefer to be matched to somebody and therefore each other than this. Yeah, okay. So this condition basically says that non-maximal matchings cannot be stable, right? Okay. All right. Now, here is the condition. What are we actually saying here? For every pair M and W which is acceptable, if you want to think in terms of the graph, this is an edge in the graph. We want this condition to be at least 1. So what this means is, from the man M's perspective, he is looking at all those women he prefers more than W. And from the woman's perspective, she is also considering all those men she prefers more than M. Now, if M and W are not matched to each other, meaning this quantity XMW, this variable is 0, or rather this matrix entry is 0, then at least this quantity and this quantity should be more than 0. And in the integral case, so if this is 0, then either this or this, at least one of them should be 1. Correct? That means that M and W are not forming a blocking pair. Straightforward? Okay. So that's what we define this as. A matrix X which satisfies these are what we call matching constraints. Okay? This is the individual rationality constraint, which is that you don't get matched to people you don't find acceptable. And this is the stability constraint. Okay? Right. Okay. So, right, this thing stays. So let X be a matching as defined before. We can easily see that X is stable if and only if X satisfies 4 and 5. 4 is that unacceptability, like if you're not unacceptable, it's 0, and 5 is the blocking pair condition that we just now discussed. Okay. Now, if you have Now we can say something more, okay. So okay. So S capital Mx, this set consists of all those rows, or rather all those male agents who get at least a non-zero valuation from one of the women. Meaning in this matrix X, let's think in terms of matrix only, that will be helpful. In this matrix X, all those rows which have at least one non-zero element, they are what this SMX is. So this condition when read like this means if you are looking at a row which has no non-zero entries, meaning this man has basically gone unmatched, right? That's the only way to interpret. If this happens, or it's the case that this man M is in SMX, but this woman, okay, this should be an M missing. Yeah, okay. So this is among the rows of, can I write here? Can you all see, because stuff is going to come here. This is the row. Look at, so this man has ranked all the women who are acceptable, who are in his preference list as in a strict order, right? So among those women, see the one, look at the entry that has a non-zero element and gets the highest ranking from M. That's who this is. Okay? So man M is saying this woman W is at least as good as the best partner I have received so far. Okay?
What is SMX?
Okay, SMX are the entries in the mth row which actually have a non-zero entry. Meaning these are the women with whom M is matched.
Non-zero means one only.
In this case, we can think in terms of fractional also. It still would make sense. But okay, we can think in terms of integer values for now. That's also okay. So this man, in this definition, it would be that he, see the point is this thing sort of loses a bit of value if we only think about integers 0 and 1, because then you only get matched to one person. So there is no point, there is no meaning in saying like among the people I am matched to, I am ranking whoever I am matched to the first. So this sort of loses, but still you can parse this condition. If this happens, that either man goes unmatched completely, like he has nobody in his row which is assigned non-zero, or he gets matched but there exists a woman, but this woman W, he likes her at least as much as the best fractional partner he has, then it must be the case that this woman is fully assigned to the available partners, like her capacity 1 is completely exhausted. So it's like saying I have bunch of temporary jobs. There is one employee who really likes me and would like me to come and work for them, and I'm better than whoever is working for them currently, but I am completely maxed out over my 8-hour workday. Okay? So that's how one would interpret this. Is it clear? Okay. Okay, and she is not only completely maxed out, but her least preferred fractionally matched partner is at least as good as this person M who would like to be matched to her. So in the temp job scenario, the jobs that are I am not only maxed out for my 8-hour work shift, but every job I have, I like it at least as much as that job that would really like to have me. So in that case, there is no blocking pair, right? Blocking pair is this thing that these two, both of them would like to be matched to each other and are available, somehow not being matched because they are occupied with something else. In this case, I can't be given more job because I am already maxed out. This adds up to 1, and additionally every job that has been currently assigned to me, I like it at least as much as that job, right? So this is basically, this ensures that M and W are not forming a blocking pair. Okay, if you think about it a bit, I think it will be clear. And, okay, now this has to go. This has disappeared. Okay. All right. So now, if this happens, that man again gets assigned. He has received some fractional assignment, and this woman here, the edge that we are the pair that we are considering, happens to be the woman that he likes the most. That's what this W star means. That this is his top preference among the people he has been assigned. So in this case, we are talking where M is actually matched fractionally to this woman W. In that case, it should be it implies, this is if and only if condition. Okay, so what this means is that this implies that this woman again is completely maxed out, like there is no additional weight you can give her, like you can't assign more, and this man is, it should be at least as good as her least liked partner. That's what this should be. It should not be equal. Okay? All right. Okay, so what this means is, so 1 to 5, so I'm sorry, for this particular part of this thing, there will be a bit of equations that you kind of have to keep in your head. So don't remember the equation, but keep what it actually means, okay. So 1 to 5 means from lemma 1 that you actually have a stable assignment. The matrix you have has a stable matching property, and if that is the case, then we are saying these properties hold true. That this one holds, this will imply this, that we just now saw, and this will, if and only if, imply this. Okay. Now, it turns out if this constraint is tight, when I say tight, I means equality holds. So what is this constraint telling me? It's saying for this man and woman pair, from the man's perspective, consider all those women he likes strictly more than this W. These contribute. That this summation basically tells me how much and how much fraction of those women are assigned to him. This says this quantity is the same quantity but from the perspective of the woman, W, and this is whether and or not they are at all matched to each other. If this is actually equal to 1, then it turns out this direction also holds. If this holds, then this direction will also hold. So this, I tell you, if you just spend a bit of time with the constraints and so on, you will be able to see why this is true. Okay. Okay, any questions so far? And finally, this is true, that if a man is at all fractionally assigned to people, like he has received any assignment, you might as well make all the constraint tight. Like so if I am going to be working, right, you might as well give me an 8-hour shift job and don't leave me for like 6 hours and like 2 hours I have nothing to do. Okay? Alright, and of course, if this is true, then this must obviously be true. This direction is trivial, right? It's this part that's this thing. And this holds from the fact that if this is strictly less than 1, well then you could have assigned somebody to this man M without violating somebody's constraint and so on and so forth. So this tightness should be automatic if this man gets any assignment at all. Now notice, this is said when you might have some unacceptable pairs, not the traditional Gale-Shapley setting where everybody ranks everybody from the opposite side, right. So if that were to be the case where there are no unacceptable partners, can we say something more here? Okay, so this you will have an analogous lemma obviously from the perspective of the women. So yeah, so just think as to what I asked. So of course I'm going to address it, but that's something to think about because now, okay, so just let's go back one step. So let's, for this motion, if you cannot imagine what the fractional thing looks like, think in terms of integers, okay? And let's just rediscover all the results, or not some of the results that we saw yesterday, but from this sort of a perspective. Here there is no Gale-Shapley running, there is no algorithmic perspective, it's just a mathematical programming formulation. I hope at least you see that there is a significant difference in the way we are looking at the problems, right? So if you don't, let's think just in terms of 0, 1 values, right? So from the point of view of 0, 1 value, SMX basically says it's this M is matched or unmatched. If M is part of this SMX set, it means there is at least one non-zero value in the row corresponding to M, and that non-zero value has to be 1 and nothing else can be more than 0. So this is what this is, right? The man M is integrally matched to somebody. And this basically would mean that if you either M and W are matched to each other, or this either M is matched to somebody significantly better, not significantly, strictly better than W, or at least W should be matched to somebody better than M. That's the standard stable pair blocking pair condition, at least avoiding blocking pair. So this is the this means when M is completely unmatched, this is when M is matched, but W is at least better than whoever his current partner is, this man M's current partner is, then it implies, so why didn't W get matched to M? Well, it must be because she is definitely matched to somebody and that person is at least as good as M, right? Okay. Now, so naturally from the women's perspective you can have the exact same analogous result and that should not be surprising. So now let's look at this result and you tell me if you can recognize this as something you've seen yesterday, okay. So we have two matchings X and Y, the same thing, the matrix matching. I defined two sets, okay. One is this Kx, K is either a man or a woman such that K prefers the outcome in X than the outcome in Y. If K gets the exact same partner in X and Y, he or she is not in this set Kx or Ky. Okay, so just process this definition for a minute. Okay, so I am just breaking the set of people who have different partners in X and Y into set Kx and Ky based on which matching they like. Okay, all right. Now we say that this W function is literally telling us under this matching X, whatever value you place here, right, this person gets matched to whom under the matching X. That's what this is, like an assignment function, okay. This X maps the men who are in Kx to the women, okay. You read this and tell me what do you think this result implies. I was going to just give away. I am at least checking whether you remember anything from yesterday and if you are alert right now. So, one, very happy to see multiple answers. Please raise your hand. You started speaking? Okay, she gets to speak for a minute, then you. Okay.
A man who is there in K of X, then the partner of the man should be in K of Y.
Yes, okay.
So we can get a mapping from vertex in K of X to the person in K of Y.
Yes, that would be the English reading of this. That's correct. That's what I was going to actually say. Now, do you recognize this result as something you saw yesterday? Okay.
Function W.
Function W is telling me it's the literally who under the matching X you place somebody A here, let's say small a. It tells you agent A got matched to whom in the matching X. Okay, so it's like an indicator function, like who did you get matched to under the matching X, and similarly for Y. So do you want to say what this result resembles?
It looks very similar. I don't know, but a kind of
Okay.
conclusion I am getting by seeing it looks like rotation.
No. Girija?
For every match, there is one partner X matching X with another X.
Tell a little louder.
For every match page, if one side X, again the other one like X, the other matching and then popularity.
Yes, that's basically this thing. That remember we said whenever I am comparing two stable matchings, M and M prime, and I look at if the man M prefers M, then his partner in M, in the matching M, would prefer M prime. That's exactly what this is. And this is a very famous result when it came, it's Knuth's decomposition result, and it came out in 76. Today it may not mean too much. I mean, you've seen this sort of thing in different versions. Basically, this is what establishes that the men and women have very competing viewpoints. And that really is the result that leads to us saying that every stable matching is also popular. I think you said this in today's talk, right? This allows us to say for if I were to do vote counting, right? If a woman says she prefers M, then the other stable matching, her partner in M would actually prefer M prime. This is why all stable matchings are equally popular. Okay, I mean that's an implication of this, and this is what this result is. Okay, so now we come to, I mean something that if you have not seen it, it may surprise you, it may sort of, it's a different way of looking at these linear constraints and what they are trying to do, okay. Anybody has taken a course on linear programming or mathematical optimization and things of that nature? Okay. Fine. Let's say, so you know what a convex set is, right? So this is the mathematical definition of a convex set, but broadly speaking, intuitively speaking, it's basically a set where if you take any 2 points in the set and draw a straight line connecting those 2 points, that line is entirely contained within the set. Okay? So you don't have these weird cutout pieces like, so this is a convex set. This on the other hand is not a convex set, because see, I can take a point x and y, and if I draw a straight line, it leaves the set. Okay? This is what a convex set is. everybody on the other side in the preference list, can you see why a stable matching will always be complete, will always be perfect? Say that that's good to prove. Like, what's the argument towards that? Suppose somebody is unmatched.
Suppose somebody is unmatched and we have the entire preference list. That means we have got every single person in that preference list and they are already matched to someone they are preferred more. Then it will be more like having less number of different other sides.
Correct. And that's another important aspect of case study that I conveniently left out. The border. Case study doesn't just have complete preferences, but the both sides are equal. So if you're taking somebody unmatched on the men's side, it means there is somebody unmatched on the women's side. And they are in each other's preferences. So they could very easily match to each other, otherwise while it's the maximality condition and therefore also the same way. Right? That's the point. This is why these constraints all become tight when we have the complete preference case. Okay, so that's the annual thing. And now we can say that if the preferences are complete and the number of men and the number of women are same, that is just as important thing. Then this assignment matrix this matching matrix that we will be talking about, that satisfies the condition 1 to 5, also would satisfy conditions 1 prime, 2 prime, 3 and this condition 5. So what can we leave out? So it seems like there are 5 constraints here and something is missing here. So what did we leave out?
The rest of the 0.
Which one?
Equation 4.
Yes, because there are no, everybody,
Is either assigned or not?
oh I'm sorry, this should be m cross w minus a. I'm sorry, this is a typo, okay? So this is, yeah, it doesn't make sense. Okay, this is this. We are talking about all those pairs that are not in the acceptable. Exactly. Because everybody is acceptable to everybody because we have complete preference list. Obviously condition 4 is redundant, right? So this direction at least is trivial. Why is the other direction straightforward as well? See, if these 4 conditions are true, these are even stronger version. This is saying at most 1. This is equal to 1 already. Yeah, there are no unacceptable pairs. So this is trivially constraint is true. It's backwards to true constraint. So basically 1, 2 prime, 3 and 5 directly imply 1, 2 and 5. 1, 2, 4, 3, 4 and 5. The more important thing is that this case, that everybody, the entire M set is matched. Which is what the HAP also says, right? That if complete preference list and sizes are equal, then everybody gets matched. Okay, so at least we get that. Now that long bunch of results that I had shown before, and I had asked, does something happen? Yes, I hope that is listening. So in the complete preference setting, where X is a matching, we say that X is stable if and only if X satisfies 5, that is literally the blocking pair condition. And that's the first result. Left with 2 prime, the modified version in the complete preference setting says. Now can you interpret this? See, there is a condition here that says if M may not be matched at all. That is gone obviously because we are in the complete preference setting. And that condition reduces to this. And what is this actually saying? That is one of the consequences of this. Correct. This actually implies that for every woman, if this is true, that M. So anyway, so when I have M here, this kind of perspective. Yeah, this is W. So that's the thing. So if all the women prefer this particular matching X among all the stable matching, because X is always stable, so this is a woman optimal matching, then it means that match, this is the man optimal, this thing, right? It's the other way. The men must like this the least. So what is the woman optimal stable matching? Is the men pessimal stable matching. That is the terminology. It's the worst possible stable matching from the men's perspective. And this one says that now, again, this is not surprising because the constraint 1, 2 prime, 3 and 5 is equivalent to 1, 2, 3, 4 and 5. So the extreme points are also equivalently characterized. The extreme points there of that polytope is the same as the extreme points here in this polytope because literally the two polytopes are equivalent. Okay?
So does that superscript and subscript just control visibility and optimality? Like
Yeah, this subscript just means from the men's perspective, this woman W is better than whoever is whoever is his best partner, or in this case his match partner in the matching X.
the W star is in superscript and M star is subscript.
Yes, this star, superscript star means the best partner among whoever is assigned, and this means the least preferred partner. Okay, maybe I didn't mention that for this thing. Okay, I'm sorry, this whole ordering has...
X.
Okay, this is the standard. Nothing, no difference happens here. These two conditions simplify because of the complete reference list scenario. Okay. Okay. This is all. This animation is off. Sorry. Okay. So now we will describe what we mean as a polytope. Okay. So you can just ignore the terminology as such. What this basically means is, notice that each of these constraints, when seen in a higher dimension, they describe hyperspace. Or if you want to think in separate two-dimensional, they are lines, if we are only dealing with this. Okay? So any point that satisfies all these constraints lies in a region that is enclosed by these planes. That region is called the polytope for this set of constraints. So throughout this time I have been saying X is a matrix or an assignment that satisfies all these constraints simultaneously. Right? So each of these constraints, if it is exactly equal to 1, it means it lies on the space, lies on the hyperplane, on the surface. When I was saying less than equal to, it was basically below the plane. If it were to be greater than, it would be above the plane. Either way, you have a constraint on the plane, below, or above. So what each of these planes does, it cuts off this whole area into two parts. Right? Actually 3 on the surface, below, above. So any point X that satisfies all these constraints, right, would be what? It simultaneously satisfies all the... If it were all less than, it could be in some kind of a bounded region. That bounded region is what is a polytope. You can think of it as a higher dimensional polygon. Okay, so that's where the thing. It's not precisely correct, but okay, for as a mental picture, that should do. Now notice one thing. This matrix X could have actually been thought. I can collapse this matrix X because in a way this matrix is this symmetric matrix, right? If M is matched to W, then W is matched to M. So the entry MW corresponds to the entry WM. So basically I just look at the entries just once and the diagonal entries are being matched to itself. They are trivially set to 0 because if you think in terms of a complete setting, right, nobody is matched matched to themselves, meaning they are nobody is single, so that's 0 anyways. So now what I have is, let's say, upper triangular matrix. Now instead of this, I can further simplify this and just extract one single vector of size E out of it, where each entry is 0 or 1 based on whether this edge is part of the matching. That is what this incidence matrix is. This incidence matrix is, and this characteristic vector captures. So there's a bit of abusive notation, but I hope you can see that saying this is equivalent to saying this, with what we have just now said, that this matrix is basically a symmetric matrix with the diagonals are 0, and therefore I can think of it as a completely a characteristic vector of E. E is the number of edges in the graph. Okay? So, and now from this perspective, so Ij is basically an edge in the graph. Okay? So now we are looking for a vector of this kind, 0, 1 vector that satisfies all these constraints. That is what we call the stable matching polydom.
Not a fractional statement matching.
Sorry?
General statement matching and not fractional. The integer statement matching and not fractional statement.
Yeah. So the relaxation that we are talking about would allow fractional, but you can think as of now this version of it is not a fraction, it's an integer solution.
Yeah. Fractional statement matching is XA not XA.
Sorry?
XMW need not be XW and fractional statement.
XMW, where is XMW? This?
How much of M is matched with W in a fraction?
Yeah. So this whole thing is slightly not very wrong. We were just supposed to see this first, then I was supposed to talk about the relaxation, the relaxed version. So when I'm saying the 0, 1, okay, when I say 0, 1, it means we are talking about integral solution. When I allow fractional values, like values between 0 and 1, then I'm talking about a fractional solution, and therefore fractional matching. Okay, so that's this thing. Yeah, okay, good point. So if you understand what he was pointing out, that's the factual point. If you didn't understand, okay, we can get to it at some point. Okay, so I think I'll take, 10 minutes break, and okay, we are already 5 minutes over time, so okay, we'll take a 10 minutes break and then we'll come back.